All right, in this video, we're going to do a introduction for gas chromatography. I believe you did talk about this topic last semester, but because this lab is focused on gas chromatography, I really wanted to review this topic, make sure we were all completely comfortable with it moving forward. Gas chromatography is used in many research labs. It's used in forensic or environmental labs. You see it a lot on TV shows. It's really used for the separation, identification, and quantitation of different compounds. So it allows you to separate, identify, and then actually detect how much of those compounds you have. All right. It's often used combined with a mass spectrometer to help identify your compounds. But in this week's lab, we're not going to be talking about mass spectrometry. We'll be doing that next week. All right. So typically, this is used for compounds that are stable enough to be vaporized. So it's normally used for small, non-polar organic molecules. So it's not really used for proteins or polymers. And sometimes you can convert polar molecules into different derivatives to make it useful. But we're really going to be just focusing on small, non-polar molecules to analyze by GC. Okay, so some basic concepts and terms we want to make sure we understand are really the terms mobile phase and stationary phase. So the mobile phase is really the liquid or gas that contains your sample and is really pushing through the stationary phase. That's called your mobile phase. In gas chromatography, your mobile phase is a gas. That's typically a non-reactive gas like helium. So your sample, right, is being injected as a gas through your column. Your column is our stationary phase, okay? And that's the phase that basically holds or, will hold your compounds back. Your compound will interact with this solid support, sort of slowing the movement down through the column. So your mobile phase is pushing, right? Your mobile phase is really pushing your compounds through the column. And then the material of the column is really helping to slow down that push. And that results in a chromatogram. So on the right here, we have a chromatogram with when different compounds have different retention times. That's when these compounds elute or come off the column into the detector. So a compound that has a short retention time, that has a small retention time, really went through the column first. So this compound I've circled in blue went through our column first. It was not really retained by the stationary phase and came out first. So that was not interacting with the column much at all. The second compound here I've circled in red has a longer retention time. So that peak is coming out second. So that was interacting with our column in a more substantial way, allowing it to not be pushed through the column as fast. Therefore, it has a longer retention time. So we're really looking at the mobile phase pushing your compound through and the stationary phase holding certain compounds back, resulting in peaks with different retention times. Here's the basic setup of a GC. Okay, so we have our carrier gas, our mobile phase, which is normal helium, right? Our sample is injected into an injection block, right, which then moves your sample through the column, which is contained in an oven. In GC, temperature is a really important factor that affects our retention times. Again, our column is our stationary phase, and that's what retains the compound as we go through. And then your compounds come out through a detector, right? So the detector will detect your compounds, right? And then we're given information of retention times and peak, okay? So these are the basic setup that we have: an injection block, a column in an oven, and a detector. And you can really set different temperatures of your injection block. You can set a temperature of your column and set the temperature of your detector. And all of those can impact your sample retention times and the amount that you see. All right. And here at the bottom, typically your injection block is around 200 degrees to make sure your sample is being evaporated. and then the detector is usually about 20 or 30 degrees above the final column temperature. But for us, you don't really have to worry about setting those temperatures. It's just making sure you pay attention to those temperatures, and we'll talk about that a little bit later. Okay, again, kind of talking about the theory of how this works, right? So we're going to be separating compounds. We're separating compounds, and compounds are generally separated in two different ways. So they can be separated based on polarities, okay? And that's kind of a direct way on how they interact with the stationary phase. Or they can be separated in an indirect way, such as a physical property like boiling point. And it turns out in GC, boiling point is a really important factor when we talk about separating our compounds, because our compounds are going to be interacting with the stationary phase more when they are a liquid and less when they are a gas. So boiling point has a big factor, especially in gas chromatography. So let's look at an example here. We have a two-component mixture. So we have two components. We're labeling these as X's and O's, right? So our mobile phase, our carrier gas is pushing those through, all right? And if we think about something like boiling point, right, something that has a higher boiling point is going to tend to be more of a liquid rather than a gas. Something with a lower boiling point will tend to be more of a gas than a liquid. So in this example, our component O probably had a lower boiling point, which means it is more of a gas, so it is not interacting with this solid support stationary phase as much. We only have a little bit of O interacting, so a lot of our O is moving forward first. So that probably has a lower boiling point, it's more of a gas, and then O will elute out first. Our compound X has a higher boiling point, so that is existing more in the liquid phase, and that's allowing that X to interact with our stationary phase more, slowing the movement down. So that is not going to move through the stationary phase as fast, which means our compound X will come out second. It will have a longer retention time, okay? So different chromatography techniques vary depending if it's more on boiling point and polarity. GC is really based on both polarity and boiling point, but boiling point is really the bigger factor when you're comparing retention times. All right? So let's summarize this again, like the vapor pressure, the boiling point, the higher the boiling point of our compound results in the compound migrating through the column slower, so higher boiling point, more liquid, it will migrate through the column slower, which means you get a longer retention time. Okay, that's really the biggest factor when we're talking about GC. All right. In other chromatographies like TLC, thin layer chromatography, polarity is a little bit more important. And again, just to talk about this concept, the more the polarities are alike, your compound and the stationary phase, the stronger their interaction will be with that stationary phase, which again would increase the retention time. Okay? And again, it's important to note out here that the column temperature also can affect this. A lower temperature of your column generally allows for more interaction of the compound with the stationary phase. Therefore, your retention times will be a little bit longer, and generally you'll have better separation. Okay, so temperature of the column can affect these retention times and separation as well. And we'll definitely see that in today's lab. Just a quick note about detectors. There's different detectors you can have. These are the three most common: flame ionization, thermal conductivity, or electron capture. And again, this doesn't really matter in this lab. I just wanted to make you aware there are different detectors that you can use in GC. It's not really a point of discussion in this lab, but I just wanted to make you aware of different detectors that you can have. So the last slide here is I just want to work through an example when we talk about identifying samples. We're really going to be talking about kind of comparing our sample versus a set of standards. So the first thing we have to really do is you have to make sure you're comparing GC runs that use the same experimental conditions. Okay, the experimental conditions will affect our retention times. So if you're trying to compare compounds, you've got to make sure you're comparing the same experimental conditions. And that's really looking at making sure the column length is the same, which is going to be common in these examples, but really making sure the column temperature, injection temperature, and detector temperature are the same. We really can't compare retention times unless these three conditions are the same when we're comparing different runs. Okay? To help identify if you have the same compounds, they will have the same retention times. So it's important that you correct our retention times. So in this example here, we've got two runs, run A and run B. So run B is our sample. A is going to be our set of standards. What I first want to do is highlight compound 1. That's going to be like our solvent / retention time standard. So this is not one of the organic compounds. In this week's lab, we're using pentane as our solvent sort of retention time standard. So that's what compound 1 is, our solvent retention time standard. And here we're really focusing on comparing, unknown compounds, right, to see if peak 2 in blue corresponds to peak 2 in black, right? So the first thing we have to do to really compare these is we have to compare the retention times. All right, and we have to apply a correction factor. So if we look at our sample B, right, this solvent retention time standard 1 has a retention time of 161. And these units could be minutes, it could be seconds. In this lab, it's generally seconds. So we see when we're comparing it to our standard run that eluted at 151. So we really need to apply a correction factor. Right? This is 10 higher, right? So to compare these, we really need to subtract these numbers, right? 161 minus 151 is a correction factor of 10. So when we're comparing our standard, that 262 is really going to look at like 252, a retention time at 252. And that peak at 312, would really correspond to a retention time of 302. All right. So when we look at these corrected retention times, right, so it's important that we correct our retention times. Again, we're going to correct using our solvent retention time standard. We've subtracted these by 10, and now we can compare these to the chromatogram A in top. So we look at this 252, well, that really looks nice and correlates to this compound 2, right? So because these numbers are similar, they're not exact, but they're very, very close. We can say that, yes, this compound 2 corresponds to that compound 2 of our set of standards. So whatever this compound 2 is, let's call it butanol, well, then we can kind of safely assume that our compound 2 meets compound 2 and is butanol. And then again, we can do that same thing for 3. We correct this retention time to 302. That clearly is very close and matches this internal standard of 3. So we can safely assume that our compound 3 matches and is the standard compound 3 run in A. So that's the first thing we want to do, is you want to make sure that you correct your retention times sort of using that solvent peak that elutes first. And in the lab, we're really using pentane to do that. Another thing you can do is ask to calculate the percent composition, right, using areas or intensities. So let's say we want to know what is the ratio, how much of compound 2 and compound 3 do we have, right? So to do that, you have to we're going to be using our intensities. Sometimes those are listed as peak areas. So it's important to remember here is that this compound 1, right, that was our pentane solvent or internal standard. We don't want to use that number. We're going to be ignoring that number. So if I want to calculate the percent composition of compound 2, I think we theoretically said that was butanol or something, you need to take a look at our area of 1400 divided by the total area. So that percent would equal 1400 divided by 1400 plus 1900. All right, so you need to divide that by the total area. If there were 3 compounds, right, we would divide it by the area of those 3 compounds. So it's just important to note we're not going to be using that area of that peak 1, that pentane standard, right? So if you calculated this here, 1400 divided by, what is that, 3300, I think that comes out to about 42.4%. Okay, 42.4%. And then obviously you could do the same for your other percentage. That would be 1900 divided by, again, 1400 plus 1900. And clearly those 2 peaks, sometimes 3 or 4 peaks, should all add up to be 100%. All right, so I've covered all the basics I really want to. I think everything here to help you understand the lab and work through the lab. Again, please email me or post any questions to the discussion board. And then, again, attend sort of our office hour class on Thursday. Thank you.